All right, hello YouTube. Today we're going to actually take the stuff that we derived last time and then use it. Which what? No. All right. So, today in particular we're going to be making sure that you're good at describing how things move with constant acceleration and specifically modeling that with math. Big goal is going to be to find the givens for the kinematic equation in any of these. Once you've got your givens squared away, pick an equation, plug it into the equation, solve it out. It's possible you'll have to use a system of equations, but highly unlikely because we've got the full 4 equations. So if you pick the right one, you won't have to use a system. That said, there are going to be times, and for the second example we do, this will be one of them, where it's a little easier to use a system of 2 easier equations instead of using the 1 harder equation. I'll show you both ways. Before we hop into that, especially if you skipped the derivation, these are the 4 equations we're going to be working with. Vx, in particular, for sort of summarizing how to use these 3 and the general steps you're going to want to take. Identify your givens. Actually, let's get this in a different color. You should wind up with at least 3 of 5. If you have at least 3 out of the 5, you're good to go, because there are 5 of these variables, and each of these equations has 4 variables in it. Pick an equation, any equation that uses the ones you want and has those 3. You want. I accidentally skipped to the next word halfway through. So the 3 that you have already, pick the equation that has those 3 and has what you're actually looking for. If you do that, you should be good to go. If you accidentally pick an equation with 2 variables, you'll hit a dead end. If that happens, don't worry about it, just pick a different equation. So if you're freaking out and you're like, the equation I picked isn't working, try another one that includes the thing you're looking for. It's not always just going to be, if you're looking for displacement, use 2 or 4. 3 has displacement in it as well, so if you don't have time, that's the more relevant thing to look for. If you don't care about time, probably use equation 3. If you don't care about final velocity, use equation 2, so on. All right. We're going to deal with a lot of word problems, so I figured it made sense. This is mostly useful as a reference sheet. I will read all of this, but in particular, you should come back, and if you're not sure how to figure out which thing from a word problem goes with which variable, this would be the way to do it. So basically, there are 5 variables. Initial velocity is going to have units of meters per second. If you see meters per second, it's going to be either initial velocity or final velocity, and it's your job to figure out which. Probably. You do have to actually read the situation. It's possible they're giving you extra information that's unrelated. If you see the object is going 5 meters per second when it starts to, that would tell you its initial velocity. If you see that it starts at rest or is dropped, either of those is giving you some hidden information. Your initial velocity is 0 because you're not moving at the beginning. So if it begins not moving, the initial velocity is 0. If you see was going 10 meters per second, went at 10 meters per second, those are both past tense, which implies that it's the beginning of the problem. Moves at 5 meters per second when, if there's a when afterwards especially, that's telling you that it was the beginning of the situation. How fast was is the question phrase that'll be asking you about what the initial velocity was. And if it's past tense, it's going to be initial velocity. And then the big ones are as far as being careful with positive or negative. If you know that it's going away from a thing, it's positive. If it's going, well, I'm not sure why I had that there. Be careful with what the positive and the negative is. If it's forward, it should be positive. If it's backwards, it should be negative. For final velocity, also going to be meters per second, that one's probably going to be either present tense, if there's a past tense piece and then there's a present tense, whichever of those two is in the future, that one is your final velocity. My camera covered it up. I almost doxed one of my friends with Steam, and it didn't happen, so that's good. Another hidden piece of information is if you see the word stops, it means that your final velocity is 0, because at the end of the problem, it's not moving. The other one that signals that whatever comes after it is a final velocity is if it's like the car speeds up to 10 meters per second or slows down to 2 meters per second. In both of those cases, because that's happening at the end, that's your final velocity. Final velocity would also be moves at either of those, depending on whether or not parts of the problem are. If parts of the problem are in past tense, the present tense will be the final velocity. If parts of the problem are future tense, the present tense will be the initial, and the future will be the final. If it's asking how fast is something going currently, how fast will something be going, anything like that, specifically if you see the words how fast, fast is going to be describing velocity. Unless it says how fast is it accelerating, unless you literally see the word accelerate or acceleration, fast is going to respond to velocity. It could, if it's asking how fast does it happen, that could maybe be asking about time. I guess just read it and double check, but mostly if you see the word fast, it's a decently safe bet that it's asking about some form of velocity. Okay. The other ones. For displacement, if you see travels and then a number, especially honestly for displacement, just look for meters. If you have units of meters, it's the displacement. If it asks you how far something went, that's going to be the displacement. If it tells you that something is 20 meters away from something, from an event, that'll either give you a position or a displacement. If you see the word goes or went, but don't see the word at, that's a good way to tell that it's talking about how far distance versus a velocity. Velocities will always have at after the goes or went. If you see going 20 meters as opposed to meters per second, you're really going to have to look at the units for that. Over the course of 20 meters, another one, make sure you're looking at the units. Acceleration is going to be probably just literally use the word accelerating. So has an acceleration of, accelerates at, slows down / brakes at, and then it'll give you an acceleration, speeds up at, and then it'll give you an acceleration. There is some hidden information in those last two, which is that if it says that it's slowing down, you know that acceleration and velocity have opposite signs. So if your initial velocity is positive and it's slowing down, make sure you make your acceleration negative. Or if you see that there are brakes kicking in, make sure that you make your acceleration negative if you make your initial velocity positive. If your initial velocity is negative and it's slowing down, make sure you make your acceleration positive. If you see that it speeds up, make sure that your acceleration and your velocity match signs. So if it previously had a negative velocity, it needs to have a negative acceleration. If it has a positive velocity, it needs to have a positive acceleration. And that'll be for if it's speeding up. Time is a lot more straightforward. The units on that one are seconds, and it's just how long does it take, or takes is the big one, or over and then an amount of time, or in and then an amount of time. Just look for the seconds, and that's time. Similarly, you can look for meters per second, and that'll be acceleration. Honestly, the weird one is just figuring out past tense versus present tense versus future tense to figure out initial versus final from velocity, because those have the same units. So after all of that, let's do a couple example problems. Which will admittedly take a minute. So we have a car is going 30 meters per second when they do a thing. So because looking at this says it used to be 30 meters per second before a thing happened. This 30 meters per second, the meters per second tells me it's a velocity. The tensing on it tells me that this is my initial velocity. So my initial velocity is 30 meters per second. When they slam on their brakes, I see brakes, so that's telling me that if this is initially positive because it's going forward, then that tells me that my acceleration is negative. And stop in 5 seconds. The stop, which is happening at the end, tells me that their final velocity is going to be 0. The 5 seconds tells me my time. So A is asking us how far do they travel in this time? How far means displacement, so we're looking for our displacement for A. And what was their acceleration? That one's hopefully a little more straightforward. Literally, it's just saying what's their acceleration, so we're looking for their acceleration for B. So let's take that, let's copy it all down, and then let's solve it out. This is unit 3.2 kinematic equations. Don't ask why the Q is capitalized. Okay, so we've got our situation where we've got our car. It's initially going with an initial velocity of 30 meters per second. I like drawing a picture because sometimes it can really help me keep track of when and where things are happening. We don't know the displacement. We're being asked for it. We know that the velocity at the end is 0. And we don't know what the acceleration is. But we do know that the acceleration is pointed backwards, so it should be negative for the final answer. And we know that the time for the whole thing is 5 seconds. So what I like to do, and you do not have to do this, but it is certainly a strategy that has worked for a lot of people who have trouble seeing how to do these problems immediately, is lay out all your variables. So every single time we do this, there's going to be delta x, there's going to be initial velocity, there's going to be final velocity, there's going to be acceleration, and there's going to be time. You don't have to write it in that order. I like putting time at the bottom for reasons that'll become relevant when we do 2 dimensions, but again, you don't have to. We know for this one that Vx is one of the things we're looking for. We know that Vx naught is plus 30 because it's forwards. We know that Vx is 0 because it's stopped at the end. And we know that our acceleration is one of the other things we're looking for, and our time is 5 seconds. So in particular, what I'm going to be looking for here, if I want to get my displacement, which is A, I want to pick an equation that has this one, this one, this one, and this one. I don't know acceleration, so I do not want an equation with acceleration. So let's write out our options somewhere on this piece of paper so that we know what to look for when we're trying to pick between them. We've got Vx equals Vx naught plus Ax times t. We've got delta x equals Vx naught t plus 1/2 Ax t squared. This one looks nice because of the delta x, but as I keep scanning through... Oh, so sorry. The first one definitely won't work because we don't have the thing we're looking for. The second one, the delta x, is tempting, especially because it's already solved for. I know that, good. I know that, good. I don't know the acceleration, so I would need to find the acceleration in order to use this one. We'll come back to it, just if we need to. Vx squared, okay, good, I know that. Vx naught squared, I know that, plus 2ax, oh, rats, don't know that, probably shouldn't use that one, times t. Times delta x, the thing we're looking for. So if I knew ax, I could use this one. And last up, we've got delta x equals Vx plus Vx naught over 2 times t. I know I want delta x, and it's already solved for, so that's great. I know Vx, I know Vx naught, I know t. This one's good to go. So we'll have delta x equals Vx plus Vx naught over 2. Again, I'm picking this one because it doesn't use the thing that I don't know and I'm not being asked about. That gives us Vx, which is 30, 0, plus Vx naught, which was 30, divided by 2, times my time, which was 5. 15 times 5 is 75. So we travel 75 meters. And that's it. Let's do B, which is going to be, I think, slightly more involved. At this point for B, if we want to, what we can do is come back up here and fill in this as 75. What's nice about that is it means that we have our displacement and we have all but one of the 5 variables. This means that any of the equations that involve acceleration will work. I'm going to pick the one that I think looks easiest, but again, any of the 3 will work. Personally, I really like this equation because nothing's squared, and that's great. So what I'll do is just write out the equation. I am going to plug in for the 0, and I'm not going to plug in for anything else yet. Just so I can get used to solving it if I didn't have numbers. The 0 is nice because it makes like the algebra significantly easier, so in general I will plug in for zeros, but if it's not like a 0, maybe a 1, but probably not. Unless it's a 0, I'm not going to plug it in. Alright, great. Zeros can also fundamentally change the way that the solution works, so sometimes it's actually really important that you plug in the 0, whereas any other number should not fundamentally change things. So that's why 0 is the only one I plug in. At this point, I'm looking for acceleration, so I just need to divide each side by time. And what that'll give me is that Vx over t is my acceleration. I know that Vx was 30. I know... Sorry, I plugged in the wrong one as 0. Let me not neaten that up. I'm just going to start from the beginning. I was like, this should be negative because I did the wrong one. Okay. This one is 0. So we've got 0 equals Vx naught plus Ax times t. I want to get rid of this Vx naught, get rid of this Vx naught. We've got negative Vx naught equals Ax times t. Divide each side by Ax, divide each side by Ax. And that'll give us negative Vx naught over Ax is equal to our time, which is negative 30 divided by... Oh, sorry, I'm looking for time. Oh my gosh. I am looking for acceleration, so this should be acceleration, this should be time. Divided by our time, which was 5, which will give us out 6 meters per second squared. Negative, which means that it was going the opposite direction of the velocity. And there's our first example. Next one's going to be a little trickier. But let's do it. So again, this one will wind up being able to solve by using one equation that's the one without the variable we don't know about, and that'll be a little bit harder than just using one of the easier equations to solve for the thing we don't know about and don't care about, and then plugging that into one of the others. In particular, basically, if you're looking at equation 2, you might have to use the quadratic, so avoiding equation 2 to solve for time tends to be a good way to go. But we will do both ways. All right, starts to slow down. So that's telling me that whatever my acceleration is, it needs to be negative. From 10 meters per second. So that from part is telling me that this is at the beginning, meaning this is my initial. Meters per second tells me that it's velocity. With an acceleration of 4 meters per second squared. All right, the meters per second squared tells me that's acceleration. The fact that it said slow down means I should throw a negative in front of here if I want to make this positive. How long, so I'm looking for time, will it take them to run 10 meters? So time is the thing I don't know. And we're being asked about a distance of 10 meters. I just realized that the AC has been on the whole time, and that's actually probably showing up in the audio, so I'm going to turn it off real quick. 1 sec. Okay, aren't you glad that I don't have any post-production on any of these and you get to see me walking over to the AC unit? Aren't you glad that I'm making it worse? Alright, let's get this copied down and actually solve it out. That one. Alright, so our givens here were, and sort of squaring away our variables again, delta x, vx, vx naught, ax, and t. I know that delta x is 10 meters. I know my final velocity is, I have no clue. I do know that my initial velocity is 10 meters per second, positive, And I do know that my acceleration is negative 4 meters per second squared. I've got no clue what my time is. Drawing out a little picture of the situation, we've got the person at the beginning, they go a distance, and then over here, they're going a lot slower for some reason. Their initial velocity is plus 10, their final velocity, we don't know, the displacement is 10 meters, the time is a thing we don't know, and the acceleration is 4 meters per second squared, backwards, so I throw the negative on it. All right. So if we're trying to solve this one out, if I go ahead and look at my equations, I know delta x, I don't know final velocity, and I don't care about it. I know the initial velocity, I know the acceleration, I am looking for time. So if I look at my available equations, I don't know Vx and don't care about it, so I'm not going to use this one. I know delta x, fine so far. I know initial velocity, fine so far. I'm looking for time, fine so far. I know the acceleration, still works, want to find time. This one will do it, and this one will do it with using only one equation. We'll have to use the quadratic equation, but this will do it. So let's do it that way, and then we'll go back and do it by solving it with two different equations for people who don't want to use the quadratic but are okay with using a system. So we've got delta x equals Vx naught times time plus 1/2 ax t squared. This one is weird because we have two different exponents on our time. Anytime you have that where you've got one of them squared and the other one not squared, the way you're going to solve it is with the quadratic equation. So I need to subtract delta x from both sides. That'll give me 0 equals delta x plus Vx naught times t plus 1/2 ax t squared. I don't know about you, but in 8th grade I learned a song to the tune of Pop Goes the Weasel for the equation form that looks like this. So if you want to try to solve the quadratic, whatever thing is free form by itself is c. So delta x is c for this one. Whatever's being multiplied by the variable that gets squared, that's b. So Vx naught is b for this one. Whatever's being multiplied by the variable that is squared is a. So 1/2 ax is a for this one. Quadratic formula is that x, which in this case is t, equals opposite b plus or minus square root b squared minus 4ac all over 2a. And then we're just going to have to fill in our stuff. So x is t. B is Vx naught plus or minus square root of b squared, Vx naught squared, plus, minus 4 times a, which is 1/2 times ax, c, which is delta x, divided by 2 times a. 2 times 1/2 times our acceleration. These 2's cancel. This 2 and this 4 become a 2. And then I just have to plug in my numbers. So we'll have that time is equal to negative Vx naught, which was 10, plus or minus, and we're going to have to figure out which after we plug in the numbers, 10 squared minus 2 times negative 4 times our displacement, which was 10 meters. That's all going to get divided by negative 4. It's calculator time. Now, looking at this really quickly, this means that there are two options. There's either an option when it was giving us a negative time, meaning before the thing happened. Actually, no, because what'll happen is if we keep this acceleration, the person will go forward, they'll slow down, and they'll come back and stop. So one of these times is going to be longer. one of these times is going to be shorter. The longer time is the amount of time it takes for them to go forward, slow down, stop, turn around, and come back to that place. We don't want that. So we want to make the time as small as possible. In order to make the time as small as possible, we want a small denominator. So we're going to want to pick the one that has the 2 with opposite signs. We want to take this -10 and make it smaller before we make it all positive. So on my calculator, I'm going to just know that I need to do the one with the addition. If you aren't sure which to pick, do both, and then pick which one you think makes sense. So in our numerator, we've got -10 plus the square root of, so I'm going to do that with parentheses, 10 squared minus 4 times 4. Oh, sorry, plus 4 times 4, because it's 4 times -4. Plus 4 times 4 times 10. All of that is getting square rooted, so to the 0.5. And then all of that is getting divided by -4. And there's our answer. The negative is a little concerning. I think that means I did it wrong. Give me a sec. Oh, I forgot the 2. So this should have been a 2, not a 4. And there's our answer. And there's another negative in there. Let's see what other exciting mistake I made. Did I have my parentheses correct? Yes, to my knowledge. Yeah, that looks good. All right. Well, were this a classroom? Oh, I found it. This delta x should be negative. This delta x should be... so this delta x should be negative, so this should be negative, so this should also be negative. So on the inside here, this should be minus, not plus, because we have the -10. And that gives us our time of 1.4 seconds. So that's how you would solve that one with the quadratic. Definitely a little wonky on with the calculator at the end. Sorry about dropping that negative. Really important that you show your work. Really important that you're able to look back at it and figure out the places that you missed. That's why. Let's do it the other way. So if you didn't like that and you were like, I do not want to have to use this confusing mess ever, that's fine. What you can do instead is pick 2 other equations. Now, we didn't use any of the equations with Vx. Well, let's try finding Vx first. How would we find Vx? Well, we use the equation that doesn't have time. And if I look, the one without time has time, doesn't have time. This one is Vx squared equals Vx naught squared plus 2a times delta x. If I plug in all my variables here, I'll get Vx squared is which I'm fine with because it's basically already solved, is equal to 10 squared plus 2 times -4 times 10. If I throw that in a calculator after remembering that I need to square root both sides, that'll give me 10 squared plus 2 times 4, which should actually be minus because it's times -4, times 10, close out my parentheses, to the 0.5, smack in the equals, and we've got 4.5. So my final velocity here is 4.5 meters per second. What's nice about this is now I can pick an equation that's easier and uses time. Personally, number 1 is the one that tends to always be easiest. So If I do that, we've got Vx equals Vx naught plus Ax times t, and I'm looking for time. Subtract off Vx naught, subtract off Vx naught. That'll give us Vx minus Vx naught equals Ax times t. Divide each side by the acceleration. Divide each side by the acceleration. Vx minus Vx naught over Ax equals t, which is 4.5 minus 10 over negative 4. I need to put the top in parentheses. And I forgot a negative, but that's fine. It's 1.4. We did get a slightly different answer without rounding, which is just because there was rounding along the way, which is why I don't tend to like plugging things in until the very end, but here we are. If you didn't plug things in until the very end, you would have actually accidentally wound up with the same equation as this one, and then that's why it's like that. You know, just saying. But that's it. So if that's a little easier, if you want to use the two equations and then use one to find the other variable instead of using specifically the second equation to find time, the second equation to find time, totally fine if the initial velocity is 0. Otherwise, kind of wonky. That's a great time to use the other thing. All right. Well, that's it from me. Thanks for watching, and goodbye, YouTube.